All right, so conditional probability and independence. Suppose you toss a fair coin twice. Define events A as the first toss is a head and B, the second toss is a head. We know that the probability of A, what's the probability of getting a head? 1/2 or 0.5. And the probability of getting B, another head, is what? Yeah, remember, it's not, they don't rely on each other. Coin can't remember what it did the first time. So what is the probability of B given A? It is the conditional probability that the second toss is a head given that the first toss is a head. The coin has no memory, we just said that. So since it has no memory, it doesn't matter. It's going to stay 1/2. They should say in this case, the probability of B given A is the same as the probability of B. Knowing that the first toss was a head does not change the probability that the second toss is a head. So let's contrast this coin toss scenario with our earlier pierced ears example. In this case, the chance process involved randomly selecting a student from a college statistics class. The events of interest were A is a male and B has pierced ears, so just reviewing what we did. What we found out was the probability of A was 90 out of 178. The probability of B was 103 out of 178. That's 103 out of 178. And the probability of B given A was 19 out of 90. We're just reviewing what we had so that you guys have your numbers right here in front of you. If we know that the chosen student is male, the probability that he has pierced ears was 19 out of 90. Remember, the probability that they have pierced, given that they were male, was 19 out of 90, which is 0.211. This conditional probability is very different from the unconditional probability. So just having pierced ears was 103 out of 178, which I put up there before, which gave you a 0.579. That a randomly selected student from the class has pierced ears. So it makes a difference to have given male to begin with. So to recap, the probability of B given A can equal the probability of B for events A and B in the coin toss setting. For the pierced ear scenario, however, the probability of B given A does not equal the probability of B. When knowledge that one event has happened does not change the likelihood that another event will happen, we'll say that the two events are independent. All right, so independent is one of those vocabulary words that you need to know. There are test questions about independence, okay? There is a probability test for independence, and we'll look at that in just a minute, but you need to be able to tell whether events are independent or not, okay? So two events, A and B, are independent. If the occurrence of one event does not change the probability that the other event will happen. In other words, events A and B are independent if the probability of A given B is the same as the probability of A. So look at this one more time. A given B is the same as A. If you're doing it the other way around, the probability of B given A, then it should be equal to whatever that first one is, the probability of B. So those are your two formulas you need to have. Honestly, it doesn't matter which one you use, okay? One or the other. So lefties down either check for independence. Is there a relationship between gender and handedness? To find out, we used a census at schools random data selector to choose an SRS of 100 Australian high school students who completed a survey. The 2A table displays data on the gender and dominant hand of each student. So are the events male and left-handed independent, and justify your answer. So we're going to call male A and left-handed B. So those are our events. It doesn't matter which formula at the top that you use. Honest to God, it does not matter. The one that I used in my notes is A given B. So just make sure if you use A given B, you're testing it against A, the very first letter that you use. All right, so this is what I'm checking. I'm checking to see if the percentages are the same. So what I'm going to do first is find that probability of A given B, which means the probability of male, given that they're left-handed. What's your given formula? Probability of male and left over probability of left. Look in your chart. Your chart's easier to use, honestly, than your tree diagram because it's just specific numbers. So male and left-handed. So look in the column and the row for male and left-handed. What do you have? 7. Just start there. 7. And then what is your probability of left-handed? So we're looking for total lefties. Total lefties. Not males, total lefties. 10, which is 70%. Everybody good? Then you're going to check your probability of A, which is the probability of male. How many males are there? Out of? So what is that probability? Yeah, 0.46. So then we're going to go back over here. Is 0.70 equal to 0.46? No. So event A and B, male and left-handed, are not independent. So what does that mean? What does that mean? Being male, given male right here, given left-handed and male, we had 70%, increases your chance of being left-handed. Left-handedness. Okay, so just being left-handed, just being male was 46 and male given left-handed was 70%. All right, we're going to flip it over. In the preceding example, we could have also compared the probability, let me see which one I did, of B given A. Oh, it's good. It's fine. You're fine. They're still seeing this. Just y'all weren't. Of B given A. With the probability of B. So we could have done both. I'm not going to do that for you. We don't have to worry about that. And then we don't need any of this right here. It's the same thing. All right. So for each chance process below, determine whether the events are independent and justify your answer. Shuffle a standard deck of cards and turn over the top card. Put it back in the deck, shuffle again, and turn over the top card. Define events A as the first card is a heart and B, second card is a heart. All right, so think about this. What are the chances that we're going to get a heart?
Is it 13 out of 52 or something?
Yeah. What did we do with that card?
Put it back.
So what are the chances that the second card is a heart?
13 out of 52.
I didn't change them, right? It's just like the coin flip. So are they independent or not? They are independent. They have the same probability. I just told you that 13 out of 52, 13 out of 52. Why is that the case? Because we replaced them. Now, if we would not have replaced it, would they be independent? No, because then it would change to 12 out of 52. Shuffle a standard deck of cards and turn over the top cards two at a time. I'm sorry, two cards one at a time. Define event A as the first card is not a heart and B as the second card is a heart.
It's not independent
Why is it not independent?
because if you have your first card as a heart, then you only have 12 out of 52 the chance of getting a heart the second time.
Okay. We changed the probability the second time. The first time we did not, we kept the probability the same. That's why they're independent. The second time we changed the probability. Those are easy to see without doing the work. The next one you actually have to do the work on. So what we just did in our example. The 28 students in Mr. Tabor's AP Stats class completed a brief survey. One of the questions asked whether each student was right or left-handed. The 2A table summarized the class data. Choose a student from the class at random. The events of interest are female and right-handed. So let me give you those. Here's your little chart. We had left-handed and right-handed, female and male. They gave this to you. It's not this is not like you had to come up with this. They handed this to you, but I didn't put it in there. Left-handed and female are 3, right-handed and female are 18. Sorry, y'all, 1 and 6. If you need to do the totals, you can do the totals. It doesn't matter. I'm not going to do them right now. So the events of interest are female and right-handed. So what do we have to do? What do we have to test? Doesn't matter which way you write it. What are the two things we're talking about? So let's say female given right-handed because that's the order you gave it to me in. What are we going to test that against?
Female.
Female, perfect. All right. So start with the given part. Remember, the given part is the probability of female and right-handed over the probability of right-handed. What is the probability of female and right-handed? 18. What about just right-handed? What's your total? 20, not 3, but 24. 18 out of 24 is 0.75. So now let's check the other side. What's your probability of female? 21. How many total students were there? 28. It said it in the problem. If we total it up, it might be easier to see. 21 out of 28 is 0.75. They are equal. What does that mean?
They're independent.
Independent. You could have also done right-handed given female compared to right-handed. It's going to come out the same exact way. So don't worry about which way you do it, as long as you come up with the same. All right, what happens to the general multiplication rule in the special case when events A and B are independent? In this case, the probability of B given A is equal to the probability of B. So that independence works. We can simplify the general multiplication rule as follows. Rachel, don't freak out. Here's another proof, okay? A and B, just like from yesterday, was the probability of A times the probability of B given A. That's what we did yesterday. So we had a hard time following the proof. But from up here, it said we can replace B given A with just B. So B given A can be replaced with the probability of B. And this is known as the multiplication rule. For independent events. If A and B are independent events, then the probability that A and B both occur is the probability of A and B, which we have been doing this whole time, so when we did California and laptops, and we multiplied those two together, we've been doing this the whole time. You just didn't know it. Almost done. Not much left. Not much writing on either page, so don't freak out that it's got a lot of space. Okay. All right, this next one, you need to know how to do this example. I know that it's on your test review, and I'm pretty sure, almost 100% sure it's on your test. Okay. So on January 28th, 1986, Space Shuttle Challenger exploded on takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets were to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring joint would function properly was 0.977. But there were 6 of these O-ring joints, and all 6 had to function properly for the shuttle to launch safely. Assuming that O-ring joints succeed or fail independently, that means one doesn't depend on the other, find the probability that the shuttle would launch safely under similar conditions. So what would have to work is that O1 and O2 and O3, I know this is boring, and O4 and O5 and O6 would have to work properly. So again, we're looking for the probability that all 6 worked. So what was the probability that O-ring 1 worked?
0.977.
Our multiplication rule said we just multiply them. What's the chance that O2 will work?
Same thing.
We're going to keep going, but how many times are we doing this?
6.
So we can reduce this to 0.977 to the 6. When we put it in our calculator, we get 0.87, which means there's an 87% chance that the shuttle would launch safely under similar conditions. So even though it's high, that 87% is still not, y'all don't like getting B's. We don't want to launch people into space with an 87% chance of it working right. The next example uses the fact that at least one and none are opposites. So we're going to flip it over. Your keywords in this one is going to be at least one, okay? So anytime you see at least one, you're doing this. Many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn the test results. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic I don't know how to say that. For example, use of rapid tests increased the percent of clients who learned their test results from 69 to 99.7%. The trade-off for fast results is that rapid tests are less accurate than slower lab tests. Applied to people who have no HIV antibodies, one rapid test has a probability about 0.004 of producing a false positive. That is, of falsely indicating that antibodies are present. If a clinic tests 200 randomly selected people who are free of HIV antibodies, what is the chance that at least one, so right here is what you need to look for. This is your keyword, at least one false positive will occur. So we want to find the probability of at least one false positive. Okay, so what we have to do first is find the probability that at least one is positive. And the way we do that is by the complement rule. Why do we have to use this? Because it says right here of producing a false positive. So we're going to subtract that and get a probability of 0.996. Guys, please pay attention to this example. Okay? So then there are 200 people, 200 people. So we take this percentage, and that's the percentage that there is no positive for 200 people is 0.4486. So one more time, what is this? This is the probability that all 200 people are negative. They do not have HIV. So then to find the probability of at least one, you then have to subtract it. Remember, at least when we were doing our probability before and we were using table, the Z table and stuff like that, we have to subtract it from one. Which gives us 0.5514. So the chance of at least one false positive in those 200 people is a 55% chance. Watch this one. It's the most missed on the test. All right, one more. The multiplication rule, the probability of A and B is the probability of A times the probability of B, holds if A and B are independent and only if they are independent. The addition rule, the probability of A or B, which is the probability of A plus the probability of B, holds if A and B are mutually exclusive. What happens if they're not mutually exclusive? What happens to the addition rule? You have to subtract the overlap. Good. Resist the temptation to use these simple rules when conditions that justify are not present. All right, so check your understanding. During World War II, the British found that the probability that a bomber is lost through enemy action on a mission over occupied Europe was 0.05. Assuming that missions are independent, so we can use those rules up there, find the probability that a bomber returns safely from 20 missions. All right. So the probability they gave us is that the bomber is lost. So what is the probability that they're safe?
0.95.
How do you get that?
Subtract it from 1.
But they went on 20 missions. So now what do I have to do?
Power to the 20.
And that gives us 3,585. Is everybody good? So watch this, watch this. Number 2. Government data shows that 8% of adults are full-time college students and that 30% of adults are age 55 or older. Because 0.08 and 0.30 is 0.025, can we conclude that about 2.4% of adults are college students 55 or older? Why or why not? So what it says is we have a probability A or an event A and an event B. And then can we conclude that 2.4%, should say of adults, sorry, are college students 55 or older? Yes or no? Why? So what does this formula imply? That they are what?
Independent.
Yes. So the formula implies independence. All right. So why is that a big deal? Why or why not?
Because you can be a college student and 55 or older.
Remember, this right here is more of a mutually exclusive definition. We don't want them to overlap. So watch what you say here. So it says being a college student and 55 or older are not independent. All you need to do is that it implies independence. You can be college and 55 or older. These events are not independent. And that's it. So just make sure that you put that they're not independent. So again, that middle statement right there, you can be college and 55 or older, is more of an mutually exclusive sentence. We don't care if they're mutually exclusive. We care if they're independent or not. Got it? Is everybody good? Sorry I took forever. I'm gonna stop sharing, stop recording.